Okay, now I'm going to talk about something called a redox reaction. You may have heard of this, maybe not. Okay. Another way to classify reactions is either by oxidation reduction or non-oxidation reduction. And so redox is just an abbreviation. It's a shorthand term that means oxidation reduction. So redox, reduction, oxidation, same thing. So redox. An oxidation reduction reaction. This is not a new concept. We just haven't put this name to it before. It's a chemical reaction where there's a transfer of electrons. Where have we seen that before? Right? If you have sodium and chlorine coming together, right? In reality, chlorine always exists this way, but what we would make is NaCl, so we'd have to have 2 and 2, right? But this idea of, now, how can I say that there's a transfer of electrons? Well, we know that this is an ionic compound, and that sodium is an ion and chloride is an ion. Sodium is +1, chloride is -1. So, this is an example. There are many examples of redox reactions. So, a non-oxidation reduction reaction is where there's no transfer of electrons. No element gains electrons and no element loses electrons. We'll see examples of these too. Okay, so here's one. Calcium and chlorine make calcium chloride. In their elemental state by themselves, they are not ions because you see there's no charge up here, right? But when they're together in a compound, we don't write the charge individually. We just know how to recognize ionic compounds and what the charges are. So we go from calcium, and over here this must be calcium 2+. This is chlorine, it becomes chloride. So this is a redox reaction. I don't know why I wrote that wrong. This one's got lots of mistakes in it. I'm sorry, guys. I'm fixing it as I go here. So electrons are transferred from calcium, which becomes Ca2+, to chlorine, which becomes Cl-. Okay. We have these two terms that I've mentioned. Redox is made up of two words. It's from reduction and oxidation. These two words mean something specific. Oxidation is the process where a reactant loses one or more electrons. So oxidation is loss of electrons. Calcium is being oxidized. Right? Calcium is being oxidized. Calcium is losing electrons. It's going from calcium to calcium 2+. The plus is the charge. You get a positive charge when you lose electrons. Reduction is exactly the opposite. Reduction is a process where a chemical gains one or more electrons. Chlorine is being reduced. It's gaining the electrons. It's going from neutral chlorine to Cl-. A way to keep these straight in your head, here's a silly mnemonic, but this is how I learned it in high school. Leo the lion says grr. Leo says grr. Loss of electrons is oxidation. Gain of electrons is reduction. There's another one that's oil rig. I don't know if that's, I don't know if that's more comfortable for you. Oxidation is loss, reduction is gain. I don't like it as well because it doesn't have the direct object there, electrons being the direct object. It doesn't say what it's a loss or gain of, but loss of electrons is oxidation, gain of electrons is reduction. That is sometimes how I remember it. When we get into oxidation numbers, there's maybe an easier way, but so oxidation numbers is a way that we're going to identify electron transfers. So the reason we need this is, okay, the loss and gain of electrons is very simple when you look at something like calcium reacting with chlorine, right? Calcium lost electrons and is oxidized, so chlorine gained them and is reduced. That's easy. But you wouldn't know by looking, you would not know by looking that this is that C3H8 plus O2 producing CO2 and H2O. You wouldn't know by looking that this is an oxidation reduction reaction as well. This is not something you would immediately be aware of, right? Because none of these are ionic compounds, so you don't think of it in that way. But there is a loss and gain of electrons going on here. So to keep track of loss and gain of electrons in something that's not quite so intuitive or not quite so familiar to us, we have a bookkeeping method called oxidation numbers. Now, oxidation numbers is fundamentally this. what we're really doing, I'm going to show you a bunch of rules that you're going to just remember, but if you ever get lost or confused as to what's going on, what we're really truly doing is when we deal with oxidation numbers, we're saying, okay, that's it. None of you are allowed to share anymore. You are not allowed to be covalently bonded. You're not allowed to share electrons in any way. You guys have to figure out who gets all the electrons in the bond. None of the sharing crap. So let's take water as a nice, simple example. Water looks like this, right? And if I say, okay, no sharing at all. You are going to be an ionic compound now. Well, we have to make a decision as to which element gets the electrons. Which element do you think should get the electrons, or would get the electrons if push came to shove? Well, the answer is the more electronegative element, oxygen. Oxygen would end up with 8 valence electrons and therefore be -2. Each of the hydrogens would be left alone with just their +1. Right? Let's look at CO2. CO2, right? We say, okay, no sharing at all. Well, oxygen's going to get all the electrons, so each oxygen is going to be -2, and carbon is going to be 4+, right? That's effectively what we're doing. I'm going to show you some rules, but now understanding where this is coming from, you'll be able to understand kind of where it breaks down and when and why it works. So like O2, there is one time when we don't make them do that. If we have like O2, and we say, okay, no sharing, they go, okay, fine. Neither of us can take the electrons away from the other, so we'll just go back to this, and we'll just be neutral. That's why elements in their pure elemental state are always going to have an oxidation number of 0. They're always considered neutral. Okay. So, this is the one I just did. CO2 is the one I just did. Okay. Here are the kind of the guidelines for how we find oxidation numbers. Okay. For elements in their standard states, just elements by themselves, O2, argon, metals like iron, just by themselves, the oxidation number is 0. It's always 0. They're neutral. Okay. This one's maybe a little weirder, but the sum of the oxidation numbers for molecules has to be 0 because molecules, by their definition, are neutral. For any compound, the oxidation numbers have to add up to be 0. The sum of the oxidation numbers for polyatomic ions has to equal the charge. Let me go through some of this. So, let me kind of explain where this would be useful. So when we dealt with CO2, right? CO2, I say, okay, well, oxygen is -2. There's 2 of them, so it's -4. Carbon is +4, right? And when we add everything up, it is, by definition, it has to be neutral. So the carbon has to be +4, the 2 oxygens have to be -4, they have to be neutral. If I dealt with NO3-, the sum of all the oxidation numbers of all the individual atoms have to add up to be -1, right? -1, because there's one extra electron hanging out on this thing. So the oxygens are all -2, so that's -6, and nitrogen is +5, as you would probably expect. I'll talk about how I know all this in a little bit, but in the next couple of rules, I'll explain how I'm doing all this. But they have to add up to be -1. So basically, the oxidation numbers for any compound, ion, or whatever have to add up to be whatever the charge on the whole thing is. Okay. Monatomic ions. This is easy. This is super easy. Calcium chloride, okay? This rule up here, number 2, tells me that the whole thing has to add up to be neutral, but that's what we do anyway, right? Ionic compounds, we already know this. Calcium is +2, chlorine is -1. There we go, we're done. It's just the charge on the ion, right? Don't get fooled. Just because you don't see the charge, you already know how to identify an ionic compound. You already know how to identify the charge on the ions in that ionic compound. So that is how you find the charge on monatomic ions. They're not going to be just sitting out like sodium plus for you. They're going to be like Na3PO4, right? So what the heck do I do with this? Well, there's a monatomic ion, sodium, and I know it's +1, right? Does that make sense? Okay. We'll go through some examples, for sure. I just want to finish. I got to finish out these rules here. Okay, next rule. Okay. Usually, it's -2 for oxygen, and it's usually +1 for hydrogen. Most cases, you're just going to go, oh, okay, hydrogen's +1, oxygen's -2. That's how for CO2, I said, okay, oxygen's -2. Now we're going to figure out what carbon is. Well, in order for the whole thing to add up to be neutral, like it has to, carbon must be +4. Right? This is a lot like what we did with ionic compounds and naming and writing formulas. Okay. There are the couple exceptions. All right. So I said usually for oxygen and +1 for hydrogen. Here's a time, how about OF2, right? If we think about this, by the rule I said, the more electronegative element always gets the electrons. Well, what's more electronegative, oxygen or fluorine? Well, fluorine wins this round because it's more electronegative. So fluorines, each of the fluorines will be -1, and oxygen will be +2, right? So when combined with fluorine, oxygen is not -2. The other time is when there's a polyatomic ion called peroxide. It's actually O2 2-, so each oxygen has a -1. The only peroxide I want you to recognize is H2O2, hydrogen peroxide. The only way this works out right is if each hydrogen is +1 and each oxygen is -1. So those are only really two exceptions. For hydrogen, the one time you'll see hydrogen not being +1 is when you see it combined with things like lithium, right? Lithium loves to lose electrons. It'll be +1. Hydrogen must be -1. That's the only other time. So when you see it combined with like group 1 and group 2 metals. But most of the time, oxygen is going to be -2 and hydrogen will be +1. Okay, so let's work on these examples. And this is supposed to be all one thing. I don't know why it didn't come out that way. So it should be N2O. Okay. Oops, there we go. So take a moment and find, I want you to figure out the oxidation number for each atom in each of the following. Okay? All right, so for N2O, what do we know? Well, oxygen's always -2, pretty much. So if this is -2 and the whole thing has to be neutral, we need +2, right? So each nitrogen must be what? Each nitrogen must be +1. Has to be. That has to be the case. Okay. How about HNO3? Okay. Well, knowing our rules for hydrogen and oxygen, this becomes easy. Hydrogen is going to be +1. Each oxygen is going to be -2. We have 6. Now, what I'm tending to do here is I'm putting the charge for an individual oxygen down here on the bottom, and I'm summing them up top. So this is +1. To get the whole thing to be neutral, nitrogen has to be +5. And so there it is. So the oxidation number for hydrogen is 1, nitrogen is 5, oxygen is -2. Okay, next. CO3 2-, carbonate. Okay, so here's the deal. For carbonate, the charge is going to have to add up to be -2. Well, we know that oxygen is -2, so that's going to be a -6. Well, this has to be +4, so carbon is +4. Easy enough. PF3. Okay, I didn't give you any rules about phosphorus and fluorine, so this can be kind of tough. This one's tricky, but remember, the more electronegative element gets what it wants. Fluorine is more electronegative, right? So what's going to happen here? Fluorine's going to be -1. So fluorine, unless it's in a molecule like F2, it's pretty much always going to be, unless it's by itself in F2, it's always going to be -1. It's always going to take electrons from something else. So it's -3. Phosphorus must be +3, +3. Which makes sense. We drew out the Lewis structure for PF3. And we said, okay, fine, nobody gets to share. All the fluorines end up with 8, right, by themselves. And since they normally have 7, right, they'll be -1, minus 1, minus 1. But phosphorus normally has 5, right? But it's only got 2 now. It's lost 3, so it's plus 3. It didn't lose these 2 because it still had its lone pair there. And then calcium chloride I already did as an example. This one should be easy. Right? Chloride is going to be minus 1, calcium will be plus 2.